Lecture 6A of Differential Equations and Linear Algebra is going to be a different kind of lecture than what we've done so far. So far we've focused on both math and physical models. In Lecture 6A, however, we're going to focus on technology use, a program called Mathematica to help us solve and understand differential equations, and difference equations for that matter. This will set us up for the rest of the semester. Now, if you don't have Mathematica, you still can get some benefit out of this lecture. For one thing, you can visit Wolfram Alpha to do some of what we do in here. That's something, a website that you can go to for free. Just Google it. You'll be able to do some of what we do in here, but just not quite everything. Another benefit, though, is you can still learn some of the math. We will take this opportunity to review the math content to some degree of lectures 1 through 5. In lecture 6B, that's a transition to linear algebra. We're going to look at linear transformations in 2 dimensions, a very beautiful geometric subject that will be very enlightening, I hope. But before we do this, I should make a few comments. First of all, I want you to note that I actually already have a YouTube playlist that you can Google or search on YouTube called Using Mathematica for ODEs. In that particular series of videos, I think it's 10 videos at the moment, I go through the Mathematica content more slowly than what I'm going to do in this lecture. I'm going to go pretty fast in this lecture. That means just like when you're listening to math lectures and you might want to pause the video and either think about something or try an example, same goes here. Since I'm going to go pretty fast, you're going to want to pause the video every once in a while and have a Mathematica session or a Wolfram Alpha session open and try what I show you. Though again, not everything will work in Wolfram Alpha. Yeah, just like I said, Wolfram Alpha is something you can use for free. It uses artificial intelligence to guess what you want. So for example, if you want to plot x squared, in Wolfram Alpha, you can just type plot x squared and it will give you a graph of x squared and some other stuff. But it may not be on the window that you want, the plotting window, and it might not look as nice as you might hope, like the axes might not be labeled the way you want. In Mathematica, we use something called the Wolfram language. This gives us power, greater precision, flexibility, and capability in what can be done. It's more exacting. You get errors if you do it wrong, but you can do more with it. You can make Mathematica do exactly what you want when you understand how to use it. So let's now go ahead and start using Mathematica for the rest of lecture A. So I've got this notebook and I'll put this in the Google Drive like usual. Mathematica files are called notebook. This is called the front end. The front end interacts with something called the kernel, which is Mathematica's engine to doing math. In this particular notebook, I've got 3 sections. The first section is labeled Fundamentals, Mathematica Fundamentals, where we'll do some basic things. This section is labeled Lectures 1 through 3, Exponential Population Growth, Separation of Variables, and Slope Fields. That was the main math content from those lectures. Separation of variables is a by-hand technique, so Mathematics is not going to actually do separation of variables, though it will solve differential equations symbolically. But we will review some models and slope fields in this section. And then finally, the last section is labeled Free Fall with Air Resistance and Euler's Method. This is essentially reviewing the last couple of lectures. And we'll show you how to implement Euler's Method in Mathematica in what I think is the most efficient way possible. You can open up these sections either by clicking on these arrows or double-clicking over here by these cells, especially when you see the little triangle like right there. You can double-click to open it up as well. But just click there. We've got more stuff that's hidden by clicking on other arrows. Under this section, you can see I've got different things that I've labeled: arithmetic, algebra, functions, graphing, and calculus. How to get Mathematica to do those kinds of things. The very first thing to realize when you want to have Mathematica do math is you need to make sure you're in input mode. You need to see a horizontal line like you see right now in wherever you might put the horizontal line. It doesn't matter where you put it. That tells you Mathematica is in input mode. If you go to the Format menu, go to Style, you'll see it's in input mode right there. If you want to change it to some other mode, like text mode, for example, you can do that. You can change it to text mode. You don't see a horizontal line anymore, but you can start typing text. This is text. And you can format it in various kinds of ways as well. But we want to do math, so let me cut this out. Notice I went to the cell over on the right and I did a Control X there to cut that out. How about doing some basic arithmetic like 2 plus 2? Okay? There I've typed 2 plus 2 where there was a horizontal line. You don't see the horizontal line anymore because I did some typing. You can see it doesn't look like text anymore. I'm about to enter this to get the answer of 4. If you've got a big long keyboard like this actually is, you can enter this once your cursor is on this cell. It doesn't matter where it's on the cell. It can be over here as well. Cell marker's right over there. Hit that enter key on the far right side of a real long keyboard. Now it takes a few seconds when you are doing your first input sometimes. That's because Mathematica is trying to get its kernel started, so to speak. It's like starting a car. Once you've done that, then it will go faster, like that. The far right enter key is not the only way to do input. More commonly, and this is what you have to do with shorter keyboards, you can do a shift enter at the same time. Notice how these things are labeled. This says input 1 and output 1. 2 plus 2 was my first input and 4 was my first output. This is labeled input 2 and output 2. Those are my second inputs and outputs. Mathematica will remember that I've done those things. Even if I go back up here and make a change, say change this 2 to a 3 and re-enter it, it will remember I've done in 1, out 1, in 2, out 2. And now when I re-enter this, it will actually be in 3 and out 3. In 1 and out 1 got erased, so to speak, at least in terms of this front-end interaction with the kernel. It's not erased in terms of the kernel's memory. It does remember that you did in 1 and out 1. And if you store a value in a variable, for example, it will remember that unless you clear the memory. And I will show you a couple different ways to clear the memory. Okay, so there's some basic arithmetic. Can we do multiplication? Sure, 4 times 17, for example. Put a star for a multiplication. Can it do division? Sure, 4 divided by 5 can do division. However, I did this on purpose. Mathematica is called a computer algebra system, and computer algebra systems treat things like this symbolically. So when I enter this, it's not going to give me a 0.8. Instead, it's going to, well, tell me what I typed essentially, 4/5. Is there a way I can get it to be a 0.8? Yes. There are a few different ways. I can type 4 divided by 5 decimal point. If you put a decimal point in there, either by the 5 or by the 4 or both, it will numerically approximate it to be 0.8, okay, as you would expect. It's not the only way to get numerical approximations. The capital N function, which is a special function in Mathematica, anytime you type a capital N by itself like this, does numerical approximations. Here's other subtleties to remember about the Wolfram language, which you need in Mathematica when you're doing it in this precise way. Functions, commands, start with capital letters, and sometimes they have other capital letters as well, so you need to pay attention to that. Another subtlety to pay attention to is inputs for functions are not parentheses, they are square brackets. And anytime you have a starting square bracket, you have to have a matching ending square bracket. Notice the little red caret there, that tells me it's wanting more input. Well, I can type 4/5 and get 0.8. You can also approximate things like pi, for example. Pi is a special number. Can I type it in Mathematica? Yes, but you've got to start with a capital letter, capital Pi. This will give a numerical approximation to pi, and the default is to 6 significant digits, which is what you see there, 3.14159 is the approximation to pi to 6 significant digits. Can I get more significant digits? Yes, you can. If your number is in an exact form like pi or a fraction, for example, without any decimal places, you can get it to any number of digits that you want within reason. I could even go, for example, to 1,000 digits of accuracy, significant digits here, and it does the calculation very quickly. There we go. There's 1,000 digits of pi. We're assuming this is accurate, that Mathematica is not lying to us. Could you do 100,000? Yeah. Could you do 1,000,000, 1,000,000,000? Well, I think there you run into some limits that we may not want to test. Okay? There could be ways around it, but we're not going to explore that at the moment. It will bog down if you make it too big. The number E is also started with a capital letter. Capital E is the number E. And we can get that to 1,000 places as well, but let's just do 100 so we can see it there in the output line. There's the number E to 100 significant digits. Okay? 99 places after the decimal. If you use a lowercase e, it won't work. If I do something like this, Mathematica doesn't think that's the number E. Notice it's even colored blue instead of black. There's a reason for that. It doesn't know what to do with it. It just says E. It's just representing a variable, a symbol. It's not assigned a value. On the other hand, I can give E a value. I can give it the value of, well, square root of 2, for example, like by typing this. Notice the square root is a function that starts with a capital S as well. And now that value is stored in the E. Notice the E changed to black. It was blue before. And now I can numerically approximate that by typing that E. But this E doesn't represent the number E, it represents the square root of 2. Okay? I can clear the memory on the number E here, or this number that the square root of 2 that I set E equal to, lowercase e. I can clear its memory. Now it changes back to blue, and now if I re-enter this, it thinks it's just a letter, okay, a variable. So lots of subtleties like that to pay attention to as well. It's not the only way to get pi and e in your input. You can go to the palettes menu and go to any of these 3 palettes. I like the writing assistant. You can use the other ones. You see essentially some buttons you can use over here that can do various things, like, for example, this button will enter a matrix, a 2x2 matrix into Mathematica. If you click this tab right here, this fancy looking thing right there, if you want to zoom in if you can, that represents the number E. If I enter that, and if I numerically approximate it, it will give me the same numerical approximation. There is a shortcut to do in Mathematica functions called postfix notation. I can apply the function capital N. Instead of using square brackets, I can put it at the end with 2 slashes like that. That will also approximate. That's another way to apply the function N. All right, that's the basics of arithmetic. What about algebra? Can I, for example, solve algebra equations? Sure. But once again, there are subtleties. Let's take a real simple one. X plus 5 equals 10. Notice I'm starting with the word solve. That's my Mathematica function that I'm using here. Capital S, it's capitalized. Notice I put a square bracket to start with, and notice the square bracket's pink instead of black. If I close that off by putting an n square bracket, it changes to black, telling me that I've closed off the square brackets. You've got to be careful here. You do not want to type the equation like this. Do not do that. X plus 5 equals 10. A single equal sign is kind of hazardous when you're trying to solve equations because it assigns values to things, and that can mess things up later on. You want to really make sure you pay attention to realize you need 2 equal signs. That's the standard way to do it in Mathematica. That's what you use when you're solving equations. Very important to pay attention to that. You want to put a comma in here in x, essentially emphasizing you're trying to solve for x, just in case there were other variables in here. Both of these things, separated by a comma, are inputs for the solve function to give me this output. X arrow 5 means the answer is x is 5. Okay? So subtleties to pay attention to: double equal signs, comma, square brackets that need to close each other off. What if I had solved for y instead of x? By the way, you can copy and paste code. Well, there is no y. So what will it do? It'll say the empty set. There is no solution for y. What if I put y in there as well as x? Maybe make this x plus y equals 10 instead of x plus 5 equals 10. Keep that a y, say. It's going to solve for y in terms of x. Y is 10 minus x, right? You can subtract x from both sides of this equation mentally to see that that's the answer. Okay? It can solve more complicated equations. I'll show you some more of that later. If you've got a complicated equation, it's often better to use FindRoot instead of solve. Solve is a symbolic approach, which doesn't always work. FindRoot uses what's called a numerical approach, which works more often, let's just put it that way. And so, for example, you could try solving this 5th degree polynomial equation. Let's just say equals 1 here for x. However, I do need to give it a guess. And this is the syntax for giving a guess. I need to put the guess right there after the comma. Notice the curvy or curly braces, I think is the more official name to call those things, go around the x and the comma, and whatever number is my guess. What should I guess is a solution to this? I'm just going to guess 0 to see what happens here. It gives me a negative answer. Negative 0.32 is an approximate root of this. Not an exact root, actually, an approximation. Okay? What about functions and graphing and calculus? This is tricky. When you define a function, like call it f of x, it'll start out blue until you've defined it, then it'll turn black. You need square brackets when defining a function, because that's what Mathematica uses instead of parentheses. The variable name goes in there, and then I purposely put this underscore there. That's not a typo. That underscore, when you are defining a function like x squared to begin with, is essential. That must be there. Okay? Otherwise, it won't work the way you want it to. Once you've defined the function, you're not going to see any output here, but the function is defined. Notice it turned black. I can now use the function. I can plug in numbers like that. If I accidentally use parentheses, it thinks I'm doing f times 3, and since f is a function, I'm not quite sure what it's going to do here. Yeah, it just tries to do 3 times f. By the way, I should mention here, back up here, if I want to solve the equation x times y equals 10, you want to make sure you put a star in there. Don't put the variables next to each other, because then it treats them like they are one variables. Variables don't have to have single letters for names. You want to make sure you put a star in there. There's another subtlety to pay attention to. So yeah, don't use parentheses for function inputs. Use square brackets. I can type f of a plus b in here as well, for example, where a and b are just symbols. It's going to square a plus b, like that. Although you might want to expand that, FOIL it. How do you do that? Well, expand is a built-in function that will do that. Notice here that I'm really applying 2 functions when I type this. An inside function and an outside function, just like with pre-calc and calculus when you use the chain rule, for example. But I'm not going to differentiate this thing. These are Mathematica functions. Well, f is defined to be x squared. Expand does the algebra. It's going to expand this expression. And I could have used postfix notation as well. I could go a plus b // f / expand as an alternative way of doing the exact same thing. Probably typically you want to stay with the square brackets. This is just for a quick thing, if you need a postfix notation to apply a function quickly. Stick with the square brackets and stick with putting functions at the beginning. But notice also the uppercase letter. I can define a function g of x to be, for example, the cosine function. However, if I do so, I need to use a capital C, because this is a built-in function. Notice this is black and this is blue. Though once I enter this, this will turn black. G of x is the cosine function, and I can now graph that. I can plot it down here, and here's how to do a basic kind of plot. Plot g of x. Notice again, once I use the function, once the function is defined, I don't need the underscore anymore. Another thing I'm using is a colon instead of just an equal sign. You can use the equal sign. Colon equals is called a set delayed operator, and don't worry about it, what it means. You can use an equal sign. I prefer by default when defining functions to use a colon. If I want to graph this from x goes from -4 to +10, this is the syntax. Notice the curly braces here again, or the curly braces. X comma, the left endpoint comma, the right endpoint is the way this syntax goes. And there is the cosine function from -4 to 10. Actually, it makes the window a little bit bigger than what you set it to be. What if I want to make the y window bigger? That can be done with an option called PlotRange. Put another comma in here and type PlotRange capital P capital R, and say we go from -5 to 5, and that will change the y direction. PlotRange can change the x direction as well, but we won't focus on that. What about calculus? Once I've got the function g of x defined, I can, for example, differentiate it like this. The derivative of cosine is negative sine. Notice the capital S and notice the square brackets. I can integrate it. I can go integrate capital I, g of x with respect to x. Integral of cosine is sine. There we go. You can use the writing assistant as well. There's an integral button here. Under the typesetting, if you click this tab here, go down here, there's an integral. Integrate g of x with respect to x to get the same answer. Okay? So use a built-in integrate function with a capital I, or use the palette, the writing assistant being one example, to get an integral sign in there. And you can do definite integrals as well. from 0 to pi, for example. By the way, another way to get the number pi in here is to do escape p escape. That makes sense. A pi, and it looks like a pi actually. Escape, double E escape does the number E. I'll show you that here in a second. But this will do a definite integral, and the answer turns out to be 0. Let's change it to be something non-zero. Let's make this up. Or say pi over 4, for example. 1 over square root of 2. By the way, that is an allowed number. You don't have to rationalize the denominator. If you want to, you can multiply the top and the bottom by square root of 2 and write this as square root of 2 over 2. But this is not like dividing by 0. It's not a mathematical sin to write it like that. And that's the way Mathematica usually does it. What's freeform input? That's essentially AI, essentially like Wolfram Alpha as well. So I can type, but to make it do freeform input, you need to type an equal sign at the beginning. And notice when I did that, it's a funny looking equal sign. This will plot x squared just like you would do on Wolfram Alpha. And it picked a plot range for me, picked a domain. It's not actually accessing Wolfram Alpha. If you want to access Wolfram Alpha, you actually do a double equal sign and it turns into a star. And I live in Minnesota. If we want to do a Wolfram Alpha search for Minnesota, I can type that. It takes a few seconds to access the server. So it's running to try to access that server to give me that information. And this is the kind of output that you would see if you type Minnesota into Wolfram Alpha. Okay, there it is. So I use double equal signs there. But I can do the same thing I did up here as well. This is a little simpler because I don't actually have to access the Wolfram Alpha server. This is just freeform input where it's using artificial intelligence. All right, on to differential equations. And difference equations for that matter. So I'm going to go pretty quick. There's a lot of content here. It will be available to you. I've shown you the fundamental basics. Okay? Now we're going to go through some stuff that's not so basic. And I pre-typed it in to save time. Okay, so you need to experiment with typing these things on your own as well. This is the very first example from the very first video, lecture 1. An unconstrained population of rabbits starts with 2 young bunnies and doubles in size every month. Represent this mathematically. Determine when the population will reach 1 million rabbits. How would I do this? Solve this problem in Mathematica? Well, first we should realize this is a difference equation, or it can be thought of as a difference equation. Pn is the population of bunnies at time n, where n is 0, 1, 2, 3, 4, etc. Pn plus 1 is the population of bunnies the next unit of time. I'm saying that is 2 times the previous population. This is called the difference equation. The initial population is 2. How can you solve that in Mathematica? Well, there are a few different ways you can do it. We can actually iterate the function that I'm essentially plugging Pn into. F of p equals 2p, or I could have called it f of x equals 2x. 2p or 2x represents the right-hand side of this difference equation, what I'm effectively plugging Pn into to get Pn plus 1. I'm iterating a function. I'm using it over and over, and NestList is the standard way to do that in Mathematica. Here I'm defining the function. Here I'm using NestList. I put the function name here first, then I put the starting value, that's 2, that's the number of bunnies at the start. Then I want to do 20 iterations. And here are the populations. So this is P0 is 2, P1 is 4, P2 is 8, P3 is 16, P4 is 32, etc. 20 iterations. I think I did forget to tell you that when you run into mistakes and you need to clear the memory, I think I forgot to tell you that it's quit kernel under the evaluation method is the thing that quits the memory. That has good benefits and bad consequences, though. If you clear the kernel to erase the memory, it's going to forget what you've done before, so you may need to re-enter a bunch of stuff. I don't want to quit the kernel, though. I can clear the function f. If I make sure I'm on an input line like that, and now f of p is not defined, but then I can re-enter this stuff. And now f is defined. Be 2p. Okay? So that's one way you can essentially solve the difference equation, or at least see the numbers that come out when you use it. What about the solution itself as a function? You need to use something called RSolve. Why R? R stands for recurrence equation. solver, RSolve. Recurrence equations are also another name for difference equations. And this is essentially the difference equation. Notice the double equal signs in there. Okay, that's essential. Don't put single equal signs. Gives me a solution. I don't have to do it with n plus 1 on the left and n on the right. I could do it alternatively with n on the left and n minus 1 on the right. If you enter that like this and enter this code here, you get the same answer. This is a form of a general solution. However, you should realize it's not the only form of the general solution. There are other general solutions. That's why I use a general solution. C is an arbitrary constant here, but here's another form of it. Instead of 2 to the n minus 1, I got 2 to the n. Another form is I could have 2 to the n plus 1. The c's would be different, depending on the initial conditions, but they are all general solutions. You can even, and I haven't mentioned this before, define these functions for negative values of n. That could be useful as well. If I have an initial value problem, IVP, I need to put two equations into RSolve inside a list with the curly braces, I can't think of the more efficient way to say it, curly braces separated by a comma. This is the difference equation. This is your initial condition, and it will solve for the unique solution in that case, 2 to the n plus 1, which I wrote symbolically like that. RSolveValue is another way to solve difference equations. Notice when you see these answers, they're in kind of a weird form, which happened with solve as well. P of n arrow, the answer. Kind of weird form. RSolveValue makes it, gives you the answer without that form. We're just looking at the function itself, so to speak, the expression that defines the function. So in a sense, RSolveValue can be nicer. And we can do it with initial value problems as well. We can define the solution. I'm calling it sol. That's my name for this function. Notice this function has more than one letter. I gave it a capital letter starting letter there, just like Mathematica's built-in functions have capital letters at the start. I actually don't have to. I mean, my f was lowercase. When you're defining functions for yourself, you don't have to capitalize. I'm doing it here. We can see the general value. We can plug in a value, like 5. 2 to the 6 is 64, for example. And we can check that it's the solution of the difference equation. How? As I've always emphasized, check that the left-hand side and right-hand side simplified to the same thing. So the solution at n plus 1, which is the left-hand side, is this for all n. And the right-hand side is 2 times Pn, 2 times sol of n. That should be the same thing. These are a match. That means this function, sol of n, is a solution of the difference equation. And I can actually test to see that these are equal by putting a double sign, equal sign in there. This will come back up. True. Those are equal. I did emphasize in the first lecture that technically speaking, sequences are only defined for whole numbers, and therefore when you plot them, you should not connect the dots. DiscretePlot does that. It plots the points without connecting the dots. It makes these vertical lines in here, which technically are not part of the graph, but it helps you see the heights better. So I typically do leave it in there. By putting extra stuff into it, into the DiscretePlot, I can make it look prettier. Don't worry about the details of how these things work. A lot of getting Mathematica to work the way you want it to is just copying and pasting what other people do, including if you go to the so-called documentation center under the help menu, you'll see examples that you can copy and paste and modify. The fundamental function we're using here is DiscretePlot. Notice DiscretePlot starts with a capital letter, and there's another capital letter in it. When you've got a function, a built-in Mathematica function that's really 2 or 3 words, it capitalizes each word at the start. We can use solve to solve equations. That's what happens here. But wait a minute, yikes! That doesn't look like a very nice answer. I'm trying to solve the problem, when does the bunny rabbit population reach 1 million? It's 1 million there. That doesn't look like a very nice answer. And what's this thing? It's an I. That's the number I, the imaginary unit. What's going on there? Mathematica is being too fancy for its own good in this case. It tries to give you the most general answer, and if you know about complex numbers that involve imaginary numbers, this is the most general answer to this equation. If we want real answers, you need to put the option reals at the end here with a capital R. And And there we get the unique real answer in exact form, which we could then approximate. Percent sign refers to the preceding output, so if I put 1% sign in there, it'll numerically approximate this thing. Okay. If I want more decimal places, and I want to refer to 2 preceding outputs, I need double percentage points, and if I want more decimal places, I can do this. I can do that in this case because this is an answer in exact form, which does bring up another issue. You see log instead of ln. Shouldn't it involve ln? Shouldn't it be log base e instead of the common logarithm? Log in Mathematica is log base e. Why do they do that? It's because mathematicians tend to think of the natural log as the best, the most important logarithm, so why not just call it log? That's the philosophy, actually. If you want a different logarithm, like log base 10, for example, like what's log base 10 of 1,000, you need an extra comma 10 in there. Oops, no, it's the other way around. Put the base first, just like you write by hand. Log base 10 of 1,000, put the 10 first. 3, because 10 to the third is 1,000. We can also store the answer in a variable. I'm calling the variable answer here. Notice it's blue. When I enter this, it becomes black. Now it's got a value stored in it, and I can see that value by typing answer and entering that. It's really got this entire thing with the curly braces and the arrow and stuff in it, stored in it, so it's not truly a number in a sense. ReplaceAll, which is I'm accessing with what's called the / dot operator, will also take the valued answer and store it now. Or return the answer as a number, okay, inside a list instead of the double list here in the arrows. That's what that does. I could have done that all at once, in fact. And I can get rid of curvy braces with this command called flatten. Flatten gets rid of curvy braces. One set of curvy braces for the first one. If I want to do the second set of curvy braces, when I did the / dot, I can use the flatten like this. Okay, flatten is a way to get rid of curvy braces. Subtle details that you probably won't remember unless you're actually trying to use them. Again, like I said before, percent sign refers to the preceding output. If I re-enter this, it's going to approximate this thing, which, okay, this is important. Let me re-enter this. If I want to approximate that to, say, 100 decimal places, I can do this again. But now if I refer to that preceding output and approximate that, even if I put a comma 100 in there, it actually doesn't do 100 decimal. Well, okay, I guess I was wrong. Usually it does 6 significant digits instead of 100. But you can get into trouble trying to get n to approximate things to any number of significant digits you want if you are representing the numbers in a non-exact form or with decimal points. I think I won't go into the details of that. These all do more different numerical approximations as well. We can use the floor function to round down. Remember, the problem is to find, in the discrete setting, the first whole number time at which the population reaches 1,000, which is actually telling me I don't want to round down this. Let's not use the floor function. Okay, the floor function will round down, but I actually want to use the ceiling function to round up. So I didn't use the right function here. In this discrete model, if I want to find the first whole number time when the population is over 1 million, I want to round up. Floor always rounds down, ceiling always rounds up. They're not rounding to the nearest whole number, they're rounding down or rounding up. As I've told you before, you can nest functions. Let's do ceiling instead of floor. And you can use postfix operators. I think I've shown you already. You can use FindRoot with a guess of 19 here. And we can use the / dot operator as well. All right, this section, we're going to look at this differential equation, which came up in the continuous model. And we're going to use DSolve to solve the differential equation instead of RSolve to solve the difference equation. Here's the syntax for DSolve. Here's the differential equation. Now, when you look at this, you do see the double equal sign, you do see the capital L log for natural log of 2. But you see something also in here that may give you pause. Like, is that really the right way to type this? If you've been watching my lecture so far, you would know that this right-hand side of this differential equation doesn't depend on t. It's an autonomous equation. And there's a good reason to not put the dependence on t in there. One good reason is to think when we think about the slope field. However, when you use this DSolve in here, I am specifying the dependence on t, both here and here. And I have a p of t there as well. Is that wrong? No, it's not. Does it make the equation non-autonomous? No, it doesn't. It's still an autonomous equation. You can still write it this way by hand. But Mathematica, in a sense, needs to know that p depends on t. There's the general solution. Constant times 2 to the t now instead of 2 to the n. This solves the differential equation, not the difference equation. And that's a general solution where c is an arbitrary constant. We can once again do initial value problems. Notice I put 2 equations in here, once again with double equal signs. The differential equation here, the initial condition here, separated by a comma, inside curly braces. That finds the unique solution of the initial value problem. DSolveValue will get rid of the curly braces, I can't stop saying curvy, and the arrow. Maybe just don't worry about whether I say curvy or curly. And solve for the general solution and the unique solution of the IVP as expressions that define the formulas. It's a simpler kind of form. And once again, we can define the solution function. There's really no difference between this function and the other one, other than the fact that I'm using a t instead of an n and imagining t to be a real number instead of a whole number, arbitrary real number. And we can check that it solves the differential equation. The left-hand side and the right-hand side simplify to the same thing. And that's a typo there. I didn't change that. This should be a differential equation. Let me just do a copy and paste here. This should be a differential equation. Okay. The left-hand side is the derivative, notice the prime. The right-hand side is natural log of 2 times the function. That is the solution, and these simplify to the same thing. Forgot to mention, I should mention, another way to do a derivative is with a capital D function. If I do this, that's syntax for taking a derivative as well. And that's helpful, especially if your function involves more than one variable and you want to emphasize which variable you are differentiating with respect to. We can make plot. That's now a continuous plot, made with plot instead of discrete plot. This is plot instead of discrete plot. It's a continuous graph. That's what we're used to. We can make it prettier with these other options. Don't worry about those things at the moment. Again, you get used to this kind of thing by copying and pasting examples. We can solve just as before. Same kind of stuff here. I mean, Mathematica doesn't know that t is a real variable that can take on any real value instead of a whole number value. So it's doing the same things it did before. Yeah. I won't bother re-entering this stuff. I should use the ceiling function here as well. Actually, if we are actually after the answer to a certain number of degree of accuracy, we might want all those decimal places. So we might not want to round in the continuous case. Let's do a different differential equation. dy dt equals ty squared. And initial value problem y of 0 is 1. But let's also make a slope field. If you were going to solve this by hand, you do want to separate variables. And notice this is a non-autonomous equation. You do see a t there. When you look at the equation in DSolve or DSolveValue, double equal signs, notice t times y of t squared. You do need a y of t in there in Mathematica, because Mathematica needs to know what is the function. Y depends on t. By hand, don't put a y of t over here, because with the slope field, that'll just confuse things. So this solves it, finds a general solution. We can compute the derivative, and the right-hand side to see that they simplify to the same thing no matter what C1 is. Mathematica is using a C1, whereas we'd be more likely to use a C. That's the left-hand side of the differential equation, the derivative of the solution. Here's the right-hand side, 2 times the solution squared. And they simplify to the same thing, left-hand side equals right-hand side. You can do it with DSolveValue for initial value problem. Sometimes the output is funny in that more naturally you'd probably want to distribute this minus sign through the bottom and write it as the bottom is 2 minus t squared. That's what I'm just mentioning here. We'd more likely write it by hand like that. And we can check that it's a solution. And also, I also check that it satisfies the initial condition by doing this syntax. I plugged in t equals 0 to see that y of 0 does equal 1. By the way, what am I doing here with the curly braces and the commas? I'm just making a list to see the outputs for each one of these all in one line, essentially. All right, now we get to the important new part. I want to make a slope field and draw some solutions in the slope field. This, again, is a non-autonomous equation. The right-hand side function is t times y squared. I can define that as a function of 2 variables, f of t comma y. Notice the underscore after both the t and the y. I can use DSolveValue again with y of t in place of y, right there. And I'm doing this for a generic initial condition. Y of 0 equals y sub 0. You've seen me do that if you've watched these lectures so far. I can enter this function. And Mathematica needs to know that it depends on both t and y0. So notice I have a t and a y0 that both with underscores. Why did I make this one a subscript instead of inside the square brackets? This is okay to do. And it's emphasizing that this is really a family of functions. There's infinitely many functions that you're considering here all at once. One function for each possible value of y0. One function of t for each value of y0. So that you think of that conceptually in your mind as an infinite family of functions, but Mathematica doesn't know that you're thinking of it that way. And if you want to allow yourself to change y0, you need to put an underscore here. But once you've done that and defined the function, now I don't need the underscore anymore. I can once again check that it solves the IVP. This is the left-hand side. This is the right-hand side when I plug the function in, and I can check the initial value as well by plugging in 0 to get these 2 things to be equal. That's why it solves the differential equation, and this is emphasizing the initial value of y is y0. What about the slope field? That's made using a command called VectorPlot. Why call it VectorPlot? Why not slope field plot or something? Well, VectorPlot is more flexible. It can allow us to do other kinds of things that we'll talk about. So here is a plot of the slope field. I have not put the solution graph in here yet. Solutions do have to follow the slope field. And you don't see horizontal lines along the t-axis, but they really would be there. There is an equilibrium solution. Y equals 0 solves the differential equation. dy dt is always 0, and t times y squared is always 0, when y itself is always 0. But solutions up here would be concave up. Solutions down here would be, well, concave down to start with, then concave up, evidently, then back to concave down. Kind of interesting. We can, well, think about the initial condition y0 equals 1 by replacing y0 with 1 here, and then we can plot that with the other plot, with that slope field. Notice plot 1, which is where I stored this slope field in a variable that I called plot 1, I didn't mention that before, is inside the show along with a regular plot. I went kind of fast on that. Show can combine graphics. Plot 1 has that other graph stored in it. Plot 2 does not. I've stored a value in plot 1, a variable I'm calling plot 1. It is a graphical variable. That graph is stored in that variable plot 1, and I can combine the graph of the slope field along with a plot of the solution where y0 is 1 by combining these with another command called show inside square brackets. So we are once again nesting these different Mathematica functions. Now I've plotted them in the same window. Kind of weird that the graph goes up here above the slope field. We can zoom in by adjusting the plot range here a bit in both the horizontal direction and the vertical direction. Okay, so there's lots of things you can do to make the graphs do what you want them to do, but you have to practice and look at examples. All right, one last section. We're going to look at free fall with error resistance and Euler's method. So again, recent lectures 4 and 5, we talked about both of those things. Free fall with error resistance, where the error resistance is a linear model, happens to be this differential equation. I've got it in these two spots with these two things that are evidently hidden here and here. We're going to take an analytic or symbolic approach in this section, and Euler's method, a numerical approach, in this section here. So this section would involve DSolve or DSolveValue. I am going to use some subscript here when I define a new function f. However, it might be good to clear the previous function, and I think that is the case here, that it's good to clear things that come before when you define a new function with the same letter but have now underscores. What are g, k, and m, and v? G is the acceleration due to gravity, which near the surface of the Earth is 9.8 meters per second squared. On the moon, it would be to something different. I want to give myself the flexibility to change these things. M is the mass in kilograms. K is a constant of proportionality in the model. If you put the m on the other side, to have essentially ma equals f, the force, k would be the constant of proportionality of the air resistance force, assuming it's proportional to the velocity, I mean in the opposite direction. V is the velocity, could be positive or negative. This is entering this function, and I can now solve the differential equation. This is my right-hand side function. Here's your differential equation, f of v, this thing is the right-hand side function. By putting the arbitrary g, k, and m in there, I can solve it for arbitrary g, k, and m. I'm also solving it for an arbitrary initial velocity. Look at this formula. Kind of a weird-looking formula. You might want to multiply this through. That can be done with expand, which I've done as a postfix operator here. Expand it out in a sort of more ordinary way. That's kind of a complicated-looking formula. I talk about the magic of copy and paste here. What do I mean by that? Well, what I mean is to get this expression here, I saved time by copying and pasting this formula down there, so I didn't have to type it all. We can define a solution function. We can plug in numbers. Notice g here is 9.8. I'm taking the k and m to both be 1, and I'm taking v0, the initial velocity, to be 20, which is what we did in lecture 5a. So see values of this function at 1 and 2. It is giving me numerical approximations by default because I'm putting the decimal in for the 9.8 there. If I change this to a 49/5, it might give me an exact answer. Yeah, involving the number e down there. So let's keep it as a 9.8, that'll be nicer. We can plug in numbers, we can plot it. One more command I'm showing you here is something called grid. With this syntax, it's going to show two plots. One, it's going to show the, based on this code here, it's going to show the slope field with a solution curve in it. This kind of syntax, just copy and paste it and maybe make adjustments. You can change the number of points that are plotted, essentially. You can change the thickness of the slope field. Probably should keep this one about the same as it is. This part down here is going to make a plot of the right-hand side function itself, which I did emphasize is an important thing to be able to do. Into two graphs, grid puts these plots side by side when using the syntax I had. Here's your solution in red in the slope field, following the slope field. Here's a graph of the right-hand side function, f of v, versus v prime, dv dt. That graph tells you about the slopes in this graph. I emphasized this in lecture 5a. For values of v where this is negative, and v is bigger than negative 9.8, the slope field has negative slopes. For values of v over here, this function, this right-hand side function, is positive outputs, v prime is positive, solutions have positive slopes. And where this is 0, which is at v equals 9.8, there is an equilibrium solution. Horizontal line segments with the slope of 0 in the slope field. It's a stable equilibrium solution. Other solutions are approaching it as t goes to infinity. That, in fact, is the terminal velocity, and this is the main mathematical point I want to make. It's also a physical point. Negative 9.8 is the terminal velocity for this model in this situation. It's predicting that if you throw this object up with an initial velocity of 20 meters per second, the velocity starts out positive but becomes negative. What that's telling you is the object is going upwards, positive velocity, but that at the moment right where you have the intercept here, 1.1 or 1.2 or so, that's where it reaches its peak, and then the velocity becomes negative, the object is going downward. But it reaches a terminal downward velocity, negative 9.8 meters per second, if this model's accurate. Now, I'm not saying if it's accurate, I'm just pretending it's accurate for a certain situation. And in general, in certain situations, it would be an accurate model, but you might have to adjust what M and K are especially. You can solve for where it equals 0. It gives a little warning here that inverse functions are being used, but this is the correct answer anyway. That's not a fatal error. We can also solve for the general solution. It turns out, though, it needs to work a little harder, and it doesn't look so pleasant. It's making some assumptions in writing this expression that are going to guarantee that this thing here, I believe, is going to be a positive number. That's why it's making these different assumptions. In these different situations, that's going to be a positive number, and that means the logarithm is going to be a real number. We want a real answer. This is the function we're after. And we can find the terminal velocity with a function called limit. 9.8. We can do it in the general case as well. Negative gm over k in general. Okay? Finally, let's look at Euler's method. So I've talked about Euler's method recently. We got this autonomous equation. We'd like to, instead of finding a formula for b as a function of t, we'd like to approximate its values. The right-hand side function is integral, key to making Euler's method work. I'm defining that as a new function here, and I am using the clear again to make sure that whatever I've entered previously doesn't mess it up. Here's a summary of what Euler's method is in this context. It's essentially, this is the main equation here. Take a previous value of v, add on the change in v, thought of as a rate of change. This is the same as dv dt times the change in time to get the new value of v. This is the way I typically do it. I create a new function based on this right-hand side function f up here that I typically call EM function. It's just the name I pick, emphasizing it's the Euler's method function. What does that mean? It means this is the function that I'm going to iterate when I use NestList. Remember, Euler's method is an iteration scheme, and it really is a difference equation. And NestList was one way that I showed you at the beginning of iterating functions. This is a different kind of function, though. This is a function that takes essentially a two-dimensional input with curly braces and gives a two-dimensional output with curly braces and commas separating the coordinates, so to speak. That's the function you want to iterate because you want to update both the value of t by delta t, which is 0.5 here, and the value of v by this quantity. Notice there's no subscripts here. There's no k's. You don't want any k's. When you use NestList, you are sort of implicitly using k's, but you don't want to actually put any k's in here. So you could double check that this is the next data point you would get with the initial condition 0, 20. By hand, if you use EM function to that, you get that next initial point, 0.5, 5.1. If we apply EM function to that, we get the next point, negative 2.35. But NestList does it more quickly, and we can even do 20 iterations in the blink of an eye instead of 2 iterations. Okay? These are data points. Points, effectively, that are not in parentheses but curly braces. The first coordinate or component is 0, then 0.5, then 1, then 1.5, then 2. The second coordinate are the v values, 20, 5.1, negative 2.35, negative 6.075, etc. And notice these numbers, the second coordinates are approaching negative 9.8. The terminal velocity. Those can be plotted with something called ListPlot, which is in effect down here, actually in a couple different ways. The first way is going to join the dots, the data points. There's the joined arrow true in there, and the second way is going to make big black dots for the data points. So I combine with show the slope field, again, Just mimic what I do there as far as those extra options in there. The plot of the solution, and that's just this one here, and a list plot both for the line segments that you see in pink and the black dots that you see. It'd be nice if we could do both of those at once, but I haven't figured out a way to do it yet. I, as a default in this course, connect the data points with straight lines, but you should realize you don't have to connect them with straight lines. And you could try to do some sort of fancier interpolation that makes the graph smooth, for example, the approximation to the true graph. Okay? That was a whirlwind tour of Mathematica and some differential equations and difference equations. If you're going to remember this stuff, you got to work on it on your own as well. Thanks for watching.